Now we get to the good part, which is hypothesis testing. Hypothesis testing in some sense is the most elementary type of inference we can perform. And as we said, hypothesis testing plays a role in most other forms of inference also. Okay, because why? Well, because inference requires us to test, right, the generalization, and there's generally some form of hypothesis test underlying that. So even though in some sense it's an important technique in and of itself, it's used in a lot of other modes of inference too. Okay, what is hypothesis testing? Well, here's the basic idea. We start off with a belief about the value of a parameter. Okay, so we know the distribution of the random variable, but we don't know one of its parameters, but we think we do. We think we have a belief about what it is. So for example, if I believe the mean of some random variable is less than 20, then mu less than 20 would be my hypothesis. Okay. There are generally 5 steps for performing a hypothesis, okay, that we have to conduct. The first is we have to state our 2 hypotheses. We have competing hypotheses. We have the hypothesis that we believe, and then we have its negation. Okay. The next we have to do is we have to calculate a test statistic. So this is going to be, in a sense, our evidence. So we think of this a lot like a court trial. The 2 hypotheses are like when a person goes to court, right? The prosecutor says guilty, and the defending attorney says innocent. They're opposite, right? There are 2 hypotheses about that person. And then you enter the evidence. Well, the test statistic is the evidence. Okay? We're going to compute from a sample a test statistic, and we're going to see which one of these 2 hypotheses is it more consistent with. Then we're going to compute the p-value for this test statistic. So the p-value is asking, in a sense, if we assume that this original hypothesis is true, how likely is it that we could have got this particular test statistic? So it's kind of like asking, if a person is innocent, what is the likelihood that all this evidence against them could happen? Okay? And then based on that, we make a decision. Okay? If the test statistic is too unlikely under this hypothesis that we believe, then we throw it away and we say the other side's correct. And then finally, we're going to state our conclusion in everyday language. We're going to actually say what we found. We're going to take all the statistics, speak out of it, and just put it in regular everyday terms. Okay, so let's look at step 1, stating the hypotheses. Basically, there are 2 main hypotheses we have, the null hypothesis and the alternative hypothesis. The null hypothesis is denoted H sub 0, null meaning 0, right? And this is the hypothesis that we believe is true. It's our belief about the parameter's value. Okay? And usually the null hypothesis is based on some sort of reasonable assumption or some sort of past data or evidence. So for example, if we were to flip a coin, what's reasonable to assume? Well, it's reasonable to assume that the probability of heads would be a half, that the coin was fair, right? So what you assume right off the bat is you assume that any coin you see is fair, right? That's the null hypothesis. Or suppose I have data on the sales of some item and the average weekly sales is $1,000. Then I would assume, based on the past history, that this week it should be $1,000. Okay? And the null hypothesis, one way of thinking about it is it's what we would believe to be true unless someone showed us evidence to the contrary. In other words, you show me a coin, I'm going to assume it's fair unless you prove otherwise, right? Sometimes the null hypothesis is also called the no news hypothesis. It's the thing that if it were true, no one would get excited about. No one would write a newspaper story about, right? If, for example, you flipped a coin 100 times and you got 50 heads, no one would write an article saying, man, finds fair coin, because that's not news, right? So the null hypothesis is kind of like the status quo. Okay? Now the alternative hypothesis is denoted by H sub 1. Sometimes people call it H sub A. Okay, I'm going to use 1 though. And it's the negation of the null hypothesis. Very often it's the thing that we're trying to prove. Okay, people used to call it the research hypothesis because it was the thing that people were trying to prove. It would be something that if it happened, it would be news. It would be something that was really exciting and not expected. Okay? So again, going back to that court analogy, the null hypothesis is like not guilty. When a person enters the courtroom initially, what do we assume about them? Well, they're assumed to be innocent until they're proven guilty, right? And the alternative is the negation. It says, no, it's guilty. And that's what we're going to be trying to be proving, right? Okay, that's the idea. Okay, so there are different types of null hypotheses we can have. Okay, first, we can look at the null hypothesis that the mean is greater than some value. So mu sub 0 is the hypothesized value. So this is the hypothesis that the mean is greater than some value. Okay? So what do we need to disprove this? Well, we need to show that the mean is a lot less than mu naught, right? So we're doing what's called a negative or left-tailed test, a negative one-tailed test or left-tailed test. Okay? In other words, in order to disprove the null hypothesis, and this should be alternative, this should be H sub 1. Whoops. Okay. Let me change all these real quick so we don't get confused. Okay. And let me just change the animation real quick here too. There we go. Okay. All right. So in order to disprove this, what the alternative has to show is that the real value of the mean is down here, right? Now we can do what's called a two-tailed test. You could claim that mu is equal to a certain value, okay? And of course the alternative is it's not equal. Well, what do we need to disprove this? Well, we need to show, in order to show it's not equal, we either have to show that it's a lot greater than mu naught or a lot less than mu naught. So here we're doing a two-tailed test. Okay? In other words, in order to disprove the null hypothesis, if we show that mu is too far from mu naught on either side, that's going to work, right? And of course, last we can have a test where we're trying to prove that the mean is less than some value. Okay? And of course, to disprove that, we have to prove that mu is greater than that value. So we're testing to see if the value is a lot larger than mu naught. And this is called a right tail or a positive one-tailed test. Okay? So these are the ways that we're going to prove these different hypotheses. We're going to see how this works out in the framework of the methodology. Okay, computing a test statistic. Okay, so here we go. Key fact is that the null hypothesis and the data collected imply the distribution for the MLE of our parameter. Okay, let me explain what that means. Let's look at an example. Suppose I collect 30 values of a random variable and the standard deviation is 3, and I'm going to assume, this is my null hypothesis, that mu is equal to 20. Okay, so if I know this and I assume this, then it follows that the distribution of the MLE estimator, which is x bar, by the central limit theorem, has a normal distribution with a mean of 20 and a standard deviation of 3 divided by the square root of 30. So what we're saying is that if this is true, then this is true. Okay, and you should think about that. Why is this true? Okay, so notice that our assumptions, so our given information and our hypothesis, imply a distribution for the MLE of the parameter we're testing. And that's very important, because now if this is true, it's almost like proof by contradiction. If this is true, then this is true, and it follows therefore that the standardized normal random variable is going to be, the standardized random variable for x bar is also going to be normal. So this means that if we have these different cases, okay, where it's normal and sigma's known, this test statistic is going to have a standard normal distribution. So this is going to be my test statistic I'm going to compute in this case, okay? And I'm implying that I know the distribution now. Given that this is true, this is a distribution of this test statistic. So I'm going to compute this from data, and I'm going to now say it comes from this distribution under the null hypothesis. Okay, if x is normal and population standard deviation is unknown, I use a sample standard deviation. And this test statistic, the standardized random variable for x bar, now has a t-distribution. Okay. If x is not normal but n is greater than 30, I can invoke the central limit theorem, right? And so this test statistic is going to be normal. This is going to come from a t-distribution. So I can't emphasize this enough, that our belief, our null hypothesis, implies a distribution for the test statistic. And now we can compute the test statistic and see how likely it is that it comes from this distribution. Okay? How do we do that? We compute the p-value. So the p-value is how likely we are to get a test statistic as extreme or more extreme than what we computed from the data in step 2. We want to know what percentile does that test statistic live in. And so we can think of it, one way to think of it, and this is very useful, we go back to those different hypotheses tests that had these tails, right? We're going to think of it as the probability in the tail of the test statistic. Alrighty? So for example, if we're doing a left-tailed test, so this is a hypothesis test where we're claiming that mu is greater than mu naught, we're testing down here. So we're going to, so this is our, suppose this is our test statistic, this is the value that we get from the data, this is our x bar from the sample minus mu divided by the standard deviation divided by the square root of n. This is the value from data. And given this is a standard normal, we're going to compute the probability in this tail. This is the p-value. Okay? It's the probability in the tail. Now if we're doing a two-tailed test, we have two tails. Okay? We have both the positive and negative value. Because remember, we're trying to disprove when we're on either side. So if we get a value this extreme or further, we have to take into account the fact that we need this area down here too. Okay. So now it's going to be the probability of twice the area in one of these tails. Okay. Because as extreme or further means the same distance or further from the mean. Well, this is the distance from the mean on this side. This is the distance from the mean on this side. So we have to account for both of them in a two-tailed test. As extreme or more extreme. So this means this distance away from the mean, but it could also have a value on this side, this distance from the mean too. Okay, for a right-tailed test, it's kind of the same as the left-tailed. Our claim here is that mu is less than mu naught, so this is what's going to make us prove that mu is greater than mu naught. This is the value of our test statistic computed from the data, our standardized random variable for x bar, and this is the area in the tail. So this is the p-value. Okay, so what do we do with the p-value? Well, how do we tell how unlikely is too unlikely? Well, we have this thing called the level of significance. It's denoted by alpha. And basically we set its value at the start of the hypothesis test. So we have to say what alpha is before we begin the hypothesis test. Actually, before we even begin collecting data, okay? And we generally use three values for alpha, 0.01, 0.05, or 0.1. And one way we can think about alpha, there's a number of different ways we can think about it. We can think about it as the minimum p-value for which the null hypothesis will not be rejected. Okay? It's the smallest p-value for which we will not reject H naught. But this tells us how to decide which hypothesis to choose. So if p is less than alpha, since p is the minimum value that we can accept the null hypothesis, and p is less than this, we're going to reject the null hypothesis. If p is greater than alpha, our p-value is greater than alpha, then we fail to reject the null hypothesis. Okay, notice something interesting. We never say that we accept the null hypothesis. We say that we fail to reject it. Go back to the criminal trial case. Okay, think about what the jury comes back and says. They either say guilty or not guilty. They never say innocent, right? Okay, they're just simply saying there wasn't enough evidence to prove he was guilty, so he's not guilty. That's what it means to fail to reject a null hypothesis. It doesn't mean that the person's innocent. It means there wasn't enough evidence to show he was guilty. In the same way, with the null hypothesis, we never say the null hypothesis is true. We simply say there wasn't enough evidence to disprove it, so we fail to reject it. Okay? So here's some homework problems I'm going to have you do, okay? Here's a couple of homework problems. And I want to go through some sample problems before you do the homework problems. I think it's going to be very useful to you. So the next video I'm going to go through the sample problems. Please do those before you do the homework problems, okay?